Okay, this is the second video. You'll forgive me. My cat. This is the video is actually set up my iPad on the cat tower, and the cat was jumping on the cat tower and hit it, and it fell over. So the video cut out. I'm not going to redo the whole thing. So we'll just kind of continue where we were. We had the harmonic series 1 over n, and we said according to the integral test, I can look at the function 1 over x, take the improper integral from 1 to infinity. And then I know I'm not going to do the integration out because we've already done it in class, but this integral diverges to infinity. So then according to the test, since the integral diverges, the series diverges. And we're done. By the same token, we'll look at the other one we were just looking at. So suppose we have the series 1 over n squared. We look at the function 1 over x squared and integrate it from 1 to infinity. Again, I'm not going to do this integral out. We already did it in class, but I know that this integral converges. I don't really care what it converges to. I just know that the integral converges. That tells me, according to the test, that the series converges. As far as it goes, we said with practice, you kind of learn which test you should do. And again, if I keep looking to the side, it's because I shooed my cats towards the window to get rid of them, and now I'm making sure that they don't try to climb out. Hopefully not, but they won't be bothering my video then. But we had said in class, with practice, you begin to learn which trick works best, which test you want to do. As far as it goes, the integral test, you need to have a function that's positive valued and decreasing for all x is greater than or equal to 1, so that you can then write out the integral and solve the integral. So basically, if you can look at the series, we know the trick to write it as a function. Just replace all the n's with x's. If you know how to integrate it, then say, oh, I can use the integral test and I'll be done. If it's a series that when you replace it with a function, you say, good Lord, I have no idea how to integrate that, then don't use the integral test. We're going to go through a few more here, but just a couple of points before we move on to the examples. Like I said, we know this integral converges. We did it in class. You can look in your notes. But I don't really care what that converges to. We did it in class. We found the value. And more to the point, it doesn't actually matter. I think it actually converges to 1 or right around 1. But keep in mind, I only care about the convergence of the series, and I don't know what this series converges to. Just because the integral converges to a number, that's the area under the curve, which is continuous. This sum is a bunch of discrete points added up, so these sums are not equal. When we worked with the integrals, we said if the integral converges, then whatever it converges to is the value of the integral. But now we're just using that trick to see if the series converges, but they're not equal to each other. We had said in class multiple times, in general, other than maybe for geometric and telescoping series, I will never know what those series converge to. All I really care about is they converge or they diverge, and that's it. So just keep that in mind as we do this. Also keep in mind, the integral test says the function has to be positive valued and decreasing for x is greater than or equal to 1. But that's a little bit subjective and can be changed a little, meaning, for the sake of argument, and I'm not going to try to pull a random series out, but we can look at it. I can just kind of make up an idea of one. Suppose I have a series, and suppose it starts here, then it goes here, then it goes there, then it goes there, then it goes here, then it goes here, and it goes down like that. That series is definitely positive valued. The sequence is, so the series would be positive valued. And it would be decreasing, clearly. Well, no, I guess it wouldn't actually. Right here it would be decreasing and then increasing and then decreasing. So we can't really use the integral test, but to a certain extent we actually can. Because we understand, while there may be a few points right at the beginning where the series, and by extension the function that we create, is not strictly decreasing, that's just a few discrete points, and I can kind of separate those off. As long as, at some point, the function and the series by extension starts decreasing, then I can apply the integral test. And basically we say, forget about those points right there. I can add them up separately. It doesn't really matter. This thing getting really small, really fast is all that really matters. The things at the beginning are irrelevant. The stuff over at infinity is what matters. Also keep in mind, this says the function has to be positive valued. But again, using the same logic, it doesn't actually have to be positive valued. You can do the same thing where the first few points maybe are negative, as long as eventually it becomes positive valued and it's decreasing and it's approaching 0, then you can use the integral test. So just be aware, this is the strict test right here, but you're allowed to kind of ease up on the restrictions a little bit, as long as you're only easing up on the stuff like close to 0, close to your starting point, close to 1. And at some point, as you approach infinity, you meet those qualifications, then you're good to go. But now, I'm not going to do the integration out because we just spent a whole chapter and you just spent a whole exam doing integration. But we can at least look at a few examples, and I'll trust that you all understand how to integrate. So, suppose we have this. The series n e to the negative n squared. I want to know if that converges or diverges. Well, can I write a positive value decreasing function that will agree with that at every point? Sure. I can let my function be x e to the negative x squared, which is clearly x over e to the x squared. And now, again, I'm not going to prove that that's decreasing, but it clearly is. Just understanding what we do about growth rates, that's exponential, that's linear. This gets bigger much, much quicker. So this whole function is going to get smaller really, really quickly. And even if there's a few points right at the beginning where it's not strictly decreasing, again, we can kind of forget about those. We know in the long run, this will dominate and it will approach 0. It will decrease. So now, I can integrate it from 1 to infinity. Here again, I am not going to integrate that. You can take the time to integrate it if you want. But clearly, again, knowing what we know and what we use when we did improper integrals, this is linear, that's exponential. This is going to get really small, really fast. This whole thing is going to approach 0 incredibly quickly, which means it's going to converge. But then that means, yes, my cats now are trying to attack squirrels by the window. Fantastic. Okay, the integral will converge, which means the series will converge. Okay, suppose we have, let's see. Well, suppose we have the series 1 over n to the 3 halves. Can I come up with a function that's positive valued and decreasing and it agrees at every end? Sure. I can just look at the function 1 over x to the 3 halves dx. Again, I can integrate that. I'm not going to. We already did this in class. And the rule we had in class was, as long as the power of x is greater than 1, then this will get small enough, fast enough that it will converge. Which then means that this series will converge. And this actually leads us to a simple rule that we are going to use that will make some of your work easier in the future. And I'll explain in a second. We have what's called p-series. And as the rule actually says, the series 1 over n to the p will converge if p is greater than 1. And the series 1 over p will diverge if p is less than or equal to 1. And this clearly comes from what we did with improper integrals before, right here. For all of these p-series, I can write a function, 1 over x to the p, then I can integrate the improper integral from 1 to infinity. But clearly, because we did it before, the integral from 1 to infinity of 1 over x to the p dx. We already said in class in the last chapter, if this p is greater than 1, then the integral will converge, which means the series will converge by the test. If this p is less than 1, the integral will diverge, which means the series will diverge by the test. So, as far as it goes from your perspective, I have said repeatedly, when it comes to exam time, you are going to have to write out all of these tests in the same way that you write out all your integrals, and you're going to have to show the test correctly, making sure you meet the conditions, in this case, positive, valued, and decreasing, even if it doesn't occur for the first few points, but occurs eventually. And then once you have that, you can then say, okay, I'll apply the integral test, so I'll come up with my function, then I'll integrate the function. You'll have to do all the integration correctly. Then say, okay, it converges or it diverges based on the integral. You are going to have to do all that work out. The one caveat that I will give you, if you end up with a series, like the series 1 over n cubed, that one you do not have to do the integral test on. That's how you would prove it converges or diverges, since it's a p-series. But I'm going to trust you understand how p-series work, because we worked with them with our improper integrals before. And you can just say, in this case, p-series, p is greater than 1, it's convergent, and you're done. If you had 1 over n, we'll say to the 3/5, you could say p-series, p less than 1, it diverges. You cannot do that for other series, like the n e to the negative n squared that we had. For those, you're going to have to do the full integral out, do all the integration, take the limit for the improper integral, everything we did before, and draw a conclusion. But for these specific cases, you can. Keep in mind, last example, if you had something like the series 2 over n squared, that is not a p-series. By definition, a p-series is 1 over n to the p. The 2 makes that not a p-series. That being said, I would allow you to say this, using my rules for series, is equal to 2 times the series 1 over n squared. This is a p-series. P is greater than 1, so it's convergent. So clearly, multiplying by 2 will still make it convergent. So just be aware of that. There is a formality to this, and you have to know the formality and be able to write everything out correctly, because if you can't, I'm going to have to mark them wrong on the test. Like I said, you now have 2 videos going over this test right here, but several examples and how it works. This test is easy because it's based off of stuff we've already done with our improper integrals before. And I'll try to set up a Zoom meeting at least once, if not multiple times next week, where we can kind of answer other questions from your homework and things like that. And I'll also make a video going through all the answers for your exam. But I'm going to wait until probably tomorrow to do that, to make sure all the exams are officially turned in and done, because I can't show you the answers until after that's done.